So in this video, we will try to understand the difference among angular acceleration, tangential acceleration and centripetal acceleration. So, when an object moves in a circular path or a rigid body rotates, we hear these terms, as far as the acceleration of the object is concerned, angular acceleration, tangential acceleration and centripetal acceleration. At times it gets confusing. At times it may appear that, angular acceleration is same as tangential acceleration. Then what is centripetal acceleration? So it's very important to declutter the relationship among these three. So to do that, let's consider an object. Let's say this car, which is moving on a circular road. So this car is having a circular motion. Now, given that this car is having a circular motion, so for a circular motion, we can use polar coordinate to locate the unique position of the car at any time t, right? So if we take the polar coordinate system, then we can uniquely locate the position of this car by two parameters. So you can see by the radius from, let's say this is the center or this is the origin. So the radius and the angle from a reference point. So we have taken this Cartesian coordinate system x and y as a, so we have taken this x axis as the axis of reference. So if we know the radius and this angular displacement theta, then we can uniquely determine the position of this car. So here theta is the angular displacement, right? Theta is the angular displacement. Then what will be the angular velocity of this car? The angular velocity will be the angular velocity, right? That will be the rate of change of theta with respect to time, rate of change of the angular displacement with respect to time. So the angular velocity will be what? D theta by dt. So the rate of change of angular displacement with respect to time. What will be the angular acceleration? So angular acceleration will be the rate of change of the angular velocity with respect to time. So the angular acceleration is denoted by alpha. So that will be d omega by dt or d square theta by dt square, right? So this is the angular acceleration, right? So this is what it is. Now, but is this the complete acceleration of this car when it is moving in a circular motion? No, right? The complete acceleration of the car is not this, right? So we have seen in one of the videos on circular motion, in one of the previous videos, that when an object moves in a circular motion, its acceleration is given by, the a vector is given by omega square r into er cap. In fact, it is minus omega square r er cap plus d dt of r omega et cap. Now, what are these ER cap and ET cap? So, ER cap, like if you would have seen that videos which I posted earlier. So, ER cap is the unit vector in the radial direction, so along the R direction, and ET cap is the unit vector in the tangential direction, right? Now, we'll come to it. Why we need to choose ER cap and ET cap? Why not? We can just use the Cartesian coordinate system. I and j. Okay, let's understand why we are using this ER cap and ET cap. The reason we are using this ER cap and ET cap is when we use this in a circular motion, the analysis becomes very easier. Why? So you see here in this equation of acceleration, if you just know the angular velocity, and let's assume that this car is moving in a circular motion, and given that the car will move in a circular motion, so the radius will be constant, right? So here this r is constant, right? In both omega square r and here r omega, r into omega and ddt of this r is constant, right? R most often it will be constant. For practical purpose, when an object moves in a circular motion, so by definition of circle, the radius is constant. Though it may not be, but for most practical purpose, the r can be constant. So only you need to know the angular velocity, right? So only if you know, if you know the angular velocity, just one parameter, then you can find the acceleration, provided r is constant, which will be in most cases. That is the case when you represent the acceleration in this manner using ER cap, the unit vectors in radial and tangential direction. But let's say if we are not using the unit vectors in ER cap and ET cap, but rather we are defining acceleration in the Cartesian coordinate system x and y, then how we will define the acceleration, or how will we define? So first, in the Cartesian coordinate system, what will be the position vector? The position vector would be what? R cos theta I cap and r sin theta j cap, right? So the r vector will be r cos theta I cap and r sin theta j cap, right? Isn't it? We will just take the components. What will be the velocity vector? We'll have to differentiate this. So let's assume that r is constant. So we will differentiate this term with respect to time. So it will be r cos d of cos theta by dt. So when you differentiate that, you will get minus sin theta d theta by dt I cap plus r sin theta will become cos theta. I'm skipping some steps, but that's what you will get, d theta by dt j cap, right? Now what is d theta by dt? This is omega angular velocity, and this is also omega angular velocity. So here if you see the velocity, to know the velocity you need to know omega. Like here also you need to know omega, but you also need to know sin theta, right? There is another term called sin theta and cos theta. So it means that to know the velocity, if you use the Cartesian coordinate system, you also need to know the value of theta. So if the object is here, I mean at any instant, if you want to find the velocity, you will need to know both angular velocity and the angular displacement, right? So it becomes a bit complex, right? But if you see in this relationship, you just need to know the angular velocity. If you know that, there is no dependency on theta, right? So that's why this relationship becomes easier. Of course, this is velocity and this is acceleration. So to find the acceleration, you will need to again differentiate this, right? As you can see, the differentiation will again become a bit complex. But in the new differentiation also for acceleration, again you will have a dependency on theta. So the point is that in Cartesian coordinate system, if you do the analysis of circular motion, you will need to know theta throughout. At any instant, if you want to find velocity and acceleration, you will need to know theta. But if you represent acceleration using the tangential and radial coordinate system, then you don't need to know theta, so the analysis becomes easier. So yeah, like we digressed, but I think this was also important to clarify. So coming back to the original discussion, so when the object moves in a circular motion, the acceleration is given by this equation, right? Now in this equation there are two terms, right? There is one component of acceleration in the negative radial direction, so you have minus omega square r, and there is one component of acceleration along the tangential direction, right? And the total when you add both these components, then you get the total acceleration, right? So total acceleration has two components, radial and tangential. Now let's look at this tangential component. So this tangential component, let's assume that it is d dt of r omega. So let's say r is constant, right? Because we told that most often r will be constant for circular motion. So if r is constant, this r will come out. So what you will have? You will have r times d omega by dt. Now what is d omega by dt? D omega by dt is alpha, right? Times et cap, right? So this is your tangential acceleration. So tangential acceleration is r times alpha. So tangential acceleration is r times angular acceleration, right? So this is now important to understand. Like this is what it is mathematically. Let's try to understand it by taking another practical example. So we have our door, right? So let's say this is our door in our room. So this is the hinge, and let's say this is our door, right? And there is a handle on the door, right? Now let's take two particles on the door, and so like how the door moves. The door moves in a circular motion, right? Or rather, the door rotates, right? So this door will move like this, right? If you move the door, it will either move like this, right? It will rotate like this. So let's take two particles on the door. One particle which is near the hinge and another particle which is at the edge, right? Now when you move the door, what will happen? Given the door is a rigid body, so both these particles on the door will move, right? So let's say you move the door from this position to this position, right? So what will happen? These particles which were here, they will move from the new position, will be this to this. Now when you rotate the door by an angle theta, or when you move the door by an angle theta, so let's say when you move the door, these two points will have, let's assume that the door is in motion, the door has some velocity, the door has some acceleration also, right? Let's assume that the door has some acceleration, so you are continuously, you are moving the door. So these 2 points will have the same angular acceleration, right? Because for both of these points, the angular acceleration will be what? The angular acceleration will be just d omega by dt, or d square theta by dt. So for each of these points, from this position to this position, the angle covered will be same, the angular velocity will be same, and the angular acceleration will be same, right? But each of these points will have different tangential acceleration, right? Because tangential acceleration depends on radius. Now this point is near to the hinge, this point is further away from the hinge, so this point will have a higher tangential acceleration than this point, right? So you're getting, right? So each of these points will have the same angular acceleration, but they will have different tangential acceleration, and the point which is farther away from the center, which has a higher radius, that will have a higher tangential velocity, or actually acceleration, and than the point which is near. And it's quite intuitive, it's quite obvious also, right? Because in the same time t, each of these points, they cover the same angular displacement, right, from here to here. But this point not linearly, but the actual distance covered by this point will be what? Will be r times theta, right? Where r is the distance of this point from the center, whereas the actual distance covered by this point will be r. So r is large times theta. So this point, while making an angular displacement of theta, actually covers a larger distance than this point, right? So obviously the acceleration, the tangential acceleration of this point will be different, will be more. So you see, so that's the difference. That's the practically you get a sense of the relationship between angular acceleration and tangential acceleration. Now the last bit is the centripetal acceleration. So as you can see, the centripetal acceleration, it is just minus omega square r er cap, right? So you see, centripetal acceleration only depends on the radius and the angular velocity, right? So for all practical purpose, if an object moves in a circular motion, right? If an object just moves in a circular motion at a constant velocity, at a constant speed, right? So if an object moves in a circular motion at a constant speed, so in the sense that the angular velocity is just constant, then the object will always have a centripetal acceleration, right? So if an object moves in a circular path at a constant speed, if an object moves in a circular path, right? It need not accelerate as it moves in the circular path. At a constant speed, let the object move. Even then, the object will have an acceleration, and that acceleration will be given by minus omega square r er cap, and that acceleration will be towards the center, right? Now again, let's intuitively think that why this acceleration should be there when the object moves in a circular path at a constant speed, rather, or even at a constant angular velocity. The reason is that when the object moves let's take any point on the object, on the locus of the object, on the motion of this object. So let's take a point here. Now at any instant, the velocity of the point is like this, right? Now what happens? This point moves in a circular path. So as it moves, the velocity, let's say it moves from here to here, the velocity changes, right? Now the velocity becomes like this. So given that its velocity changes from this direction to this direction, so there must be some force acting on it, there must be some acceleration on this point which would be towards the center, right? Which is kind of trying to push, trying to move this velocity in this direction. So there must be some external acceleration, or whatever, some acceleration towards the center, which kind of which acts towards the center and which forces this object to move like this, right? So from here, if the object moves here, then the new velocity direction will be like this. So had that external acceleration or force not been there, this object would have gone like this, right? It wouldn't have moved in a circular path, but because it was compelled to move in a circular path, so it was under the influence of some acceleration, and that acceleration was actually in this direction towards the center. So the net result of that acceleration is that the object changes its course. It doesn't go like this, it comes like this, right? The point is that when an object moves in a circular path, even at a uniform angular velocity, right, even there is no angular acceleration, still the object will have a centripetal acceleration.